Hello everyone, and welcome back to Number Theory. A brand new topic today, congruences. Let's look at a definition. Let n be a natural number greater than or equal to 2. Then we say that two integers a and b are congruent modulo n, denoted this way. It's like an equal sign, but with 3 bars instead of 2. A is congruent to B modulo n exactly when the difference of A and B is a whole number multiple of n, or A minus B equals Kn for some integer k. So if this is true for A and B, then we say that A is congruent to B modulo n, and we denote it this way. If this is not true, then we say that A and B are incongruent modulo n, and we denote it this way. Essentially, we just draw a slash through the congruence sign. Now, before we do anything else, let's just look at some examples. Let's see. If they are, then our definition says that A minus B is equal to Kn. For some integer k. So A is 21, B is 55. And if they're congruent mod 17, that's our n here. Let's see, is this the case? 21 minus 55, negative 34 is equal to, 2 times 17. So in other words, the difference of 21 and 55 is a whole number multiple of 17. And so we write "21 is congruent to 55 modulo 17. That's the way we write it. Let's look at another example. A equals 12, B equals negative 54, and N, let's see, let's have that be 6. What the heck? Is A congruent to B mod 6? Or is 12 congruent to 54 mod 6? Well, if so, then there exists some integer k such that 12 minus 54 is equal to k times 6. Let's check. Whoops, I did not do this right. I did not do this right. Did you catch what I did? If they're congruent mod 6, then there's an integer k such that their difference is equal to k times 6. Okay. 12 minus negative 54 is positive 66. And is that some integer times 6? It sure is. It's 11 times 6. So this is our integer k. The difference of 12 and negative 54 is a whole number multiple of 6. So they are congruent. 12 is congruent to negative 54 modulo 6. One more example. So are these two things congruent mod 11? 74 congruent to 39. Mod 11. If they are, then their difference is equal to some whole number multiple of 11. $74 minus 39, what is that? 35? And there's no integer that makes that happen. No integer times 11 is going to give us 35. So 74 is not congruent or is incongruent to 39 mod 11. Whoops. Let's make this an A. Let's see, how could we rewrite this? We could move the R to the other side. But this says that the difference of A and R is some whole number multiple of n. So if the difference of A and R is some whole number multiple of n, that means that A is congruent to R modulo n, oh, by the way, in this application of the division algorithm, isn't R unique? It is. R is unique. So R is unique here also. So what have we established? Given natural number n greater than or equal to 2, and any integer a there exists a unique R where R is between 0 and n minus 1, such that A is congruent to R modulo n. And this gives us another definition. both of these are true, but typically when we give a congruence of a number modulo n, we do it in terms of the least non-negative residue. Much the same way that when we write a fraction, typically we write the fraction so that the numerator and denominator are relatively prime. They have no factors in common. So technically this is correct, but since there's a common factor of 4 in top and bottom, we divide by the common factor and write it like this. This isn't incorrect, but this is preferable. And in our calculations, sometimes we'll have an expression like this. And while we're calculating, this is fine. But once we do all of our calculating, we like to have our answer in this form. Similarly, this is not incorrect. This is fine. But it's preferable to have 24 expressed in terms of a least non-negative residue modulo n. In other words, some number between 0 and, in this case, 4. Now, while we're calculating or doing calculations, we might have something like this, and that's fine. But when all the dust clears and our calculating is over, this essentially would be expressed this way. Now, let's look at something else. Now, before I prove this, let me give some examples just to illustrate what we're talking about. (21) and 46 are congruent mod 7 because their difference is a whole number multiple of 7. But there's an alternative way of establishing that these two are congruent mod 7. When we divide 25 by 7, we get a remainder of 4. When we divide 46 by 7, we get a remainder of 4. So we have the same remainder when we divide by 7, which implies that 25 is congruent to 46 mod 7. Now let's look at another example. Again, just to illustrate the point. Now let's take 29 and 52. Okay, we'll say they're not congruent mod 9. And there are two ways that we can do this. We can say that 29 minus 52 is what, 23? And 23 is not equal to some integer times 9 for any integer k. So that's one way that we can show that 29 and 52 are not congruent mod 9. Alternatively, we can use this condition or this criterion up here. If 29 and 52 are congruent, then they'll have the same remainder when we divide by 9. If 29 and 52 don't have the same remainder when we divide by 9, then they're not congruent mod 9. So let's see. 29 is equal to 3 times 9 plus a remainder of 2. 52 is equal to something. 5 times 9 plus a remainder of 7. So when we apply the division algorithm, they yield different remainders. And as a consequence, 29 is not congruent to 52 modulo 9. I think once we get used to doing congruences and modulo arithmetic, this is probably going to be the criterion that we use. We're going to take two numbers and say, okay, let's see, 29 divided by 9 is 27, remainder 2. 52 divided by 9, that's 45, remainder, okay. Remainder of 2, remainder of 7, they're not congruent mod 9. Probably more often than not, we're going to use this criterion rather than the definition. Now, we've seen some examples. Let's just show why this is the case. Let's do the proof of our theorem. So let n be greater than or equal to 2, and let a and b be integers. Okay. A congruent to b mod n implies that they have the same remainder. When we divide by n. So that's what we're going to do first. A is congruent to b mod n implies a and b have the same remainder when divided by n. So we let the hypothesis be given. That is, suppose that A is congruent to B mod n. This implies that there exists an integer k such that a minus b equals kn. Okay, where do we go now? I have absolutely no idea. Ah, okay. By the division algorithm, there are unique Q1, Q2, R1, R2, such that A equals Q1n plus R1 and B equals Q2n plus R2. Since A minus B is equal to Kn, for some integer k, this implies that A, which is Q1n plus R1, minus, oh, let's see, something else we need to say about this. R1 and R2 are both between 0 and n, greater than or equal to 0 and strictly less than n. That's going to be important, I think. Okay, so here's A, and here's B. And this is what? Kn. This whole thing is Kn for some integer k. Now, let's see. Kn is equal to Q1 minus Q2n plus R1 minus R2. And since Q1 and Q2 are also integers, I think what I'll do is I'll subtract Q1 minus Q2 from both sides. R1 minus R2. And by the way, forgive me, that should be implies. This is not equal to that. This statement implies that statement. But what about this thing? R1 and R2 are both non-negative. And we have R1 is strictly less than n. And so R1 minus R2 is definitely less than n. And then we could say similarly, R2 is less than n. And so this would imply that R2 minus R1 is definitely less than n. Now, what happens if I multiply both sides by -1? R1 minus R2 is greater than -1. R1 minus R2 is a multiple of n, a whole number multiple of n. But the only whole number multiple of n between -n and +n is 0. So we have a whole number multiple of n between -n and +n. That has to be 0. Well, what were R1 and R2? They were the remainders, respectively, when we divided A and B by n. Hence, A and B yield the same remainder. Okay, we proved it one way. Now I guess we should prove it in the opposite direction. I'll let you take a look at this for a couple more seconds before I start to erase. Okay, we have to prove this the other way. Okay, this is going to be a bit easier, I'm almost certain. I think this one's going to be a snap. So we say, let the hypothesis be given. That is, suppose A and B have the same remainder. Okay. They have the same remainder. So let's call that common remainder R. So they're unique Q1 and Q2, such that A equals Q1N plus R, and B equals Q2N plus R. So observe, A minus B is equal to Q1N minus R minus Q2N, no, Q1N plus R, I beg your pardon, Q1N plus R minus Q2N plus R, and that gives us Q1N minus Q2N, or Q1 minus Q2N. Q1 and Q2 are both integers, so this is an integer, and we'll call it K. So A minus B equals Kn for some integer K. And that's the definition of being congruent modulo n. So A is congruent to B mod n. And that's exactly what we were supposed to show. So this is an equivalent criterion for showing two numbers are congruent modulo n. If they both have the same remainder when we divide by n. Well, I'll tell you what. I should give you a little more, but I'm going to stop it right now and do another one a little bit later, do another lecture a little bit later. Stay tuned, okay?